So, good afternoon, everyone. Thank you for attending this academic lecture. This is actually our last lecture for the term. It's currently week 9 in DLSU. So, for the rest of the term, we are not going to have any lectures or workshops anymore as a lab. So, the title of the presentation for this afternoon is Exploring Multimodal Object Detection. This will be presented by Ryan Karandang. So let me read to you the abstract or what you're going to understand from this presentation. Multimodal object detection is a growing field in computer vision that leverages multiple data sources to improve object detection performance. Unlike traditional models that only rely on RGB images, multimodal object detection incorporates additional modes or modalities such as depth data, thermal data, audio data, textual information. This lecture provides an in-depth exploration of different techniques in multimodal object detection. So we're going to begin understanding some fundamental concepts in object detection and multimodality. Attendees will gain insights into core approaches and architectures for combining multimodal data through different fusion techniques. And we're also going to learn about different deep learning based fusion strategies. So all throughout the presentations, we're going to learn introduction to multimodal data, object detection, different architectures, advantages and disadvantages, and also use cases. So the speaker for this afternoon is Matthew Ryan Karandang. He is an undergraduate student at De La Salle University pursuing a degree in computer science as part of the honors program. We call it the BSMSCS program in DLSU. Currently, he is conducting his thesis research on multimodal object detection, specifically on optimizing multimodal models used in vehicle detection. So I will now give the floor to Ryan. Ryan, you may start your lecture.
Okay, so hello, good afternoon, everyone. Thank you, Sir Aaron, for that introduction. Again, I'm Matthew Ryan Karandang, and I will be talking up presenting my my lecture titled Multimode Exploring Multimodal Object Detection. So for the contents of this lecture, first we will be dabbling into the different modalities in object detection. We're gonna be talking about the difference between each other in terms of the sources of data that they use and the different strengths and limitations of each modality. We'll be then tackling introduction to multimodality, approaches and architectures, advantages and disadvantages of using multimodal object detection, and some of the use cases and applications that are currently in the field right now. So starting off with modalities in object detection, we have the most recognized one, which is camera. So camera, the plain camera is like the most commonly used in object detection, and it's one of the things that people think of when they think of object detection. So models are mostly trained on labeled images, and the these images are then features are then extracted from these images. So for object detection, uh, models usually localize bounding boxes to classify objects in 2D images. So the strengths of these of using plain camera for object using plain camera is cameras have RGB pixels in it, so it provides color and texture information. So models usually extract features from there. Yeah, so it is also easy to deploy. So since it's by far, well, out of the three that I will be mentioning, it's by far the less computationally expensive one. And there are plenty of datasets that already are focused on multiple images. These datasets are uh, have been used to benchmark different models such as MS COCO dataset, ImageNet, and Pascal Vault and such. As for the limitations of plain images, uh, there is a lack of depth perception since the models are extracting features from 2D images. There's really no depth involved in when models are extracting features. So the models cannot determine which objects are closer to the camera itself and which objects are further from it, and vice versa. So there's also uh there's frequent performance drops due to different anomalies such as occlusions. It struggles in poor lighting, and it can even struggle in adverse weather conditions and such. And in general, it is prone to changes. So moving on to the next modality, we have LiDAR. So compared to the previous modality, which is camera or plain images, LiDAR works differently in such that the LiDAR sensor basically emits uh, different beams or laser beams. And once it hits an object, it then travels back to the LiDAR sensor. And the time it takes for it to travel to the object and bounce back to the sensor is your data point. So as you can see in this GIF below, or GIF that I have included, uh, basically the LiDAR sensor is attached to the car. Then it's constantly emitting beams of light or laser. So, and it bounces off to the different objects that's being able to be being detected, such as the different cars and people walking around the road and the different buildings, and it returns to the sensor itself. So the data mainly used for LiDAR is they're called point clouds. So uh I'm not sure if you guys can see, but the each each detected car is made up of different point clouds. So each each pixel, or yeah, each pixel inside the bounding box is uh one data entry that is generated by the LiDAR sensor, and each point has uh it's like it's defined by uh, it's defined by 3D coordinates, so XYZ. So it has a sense of depth to it. So the strengths of when it comes to LiDAR is it has accurate spatial and distance measurement, since it's the distance of the sensor to the said object. There is depth perception with LiDAR. So, another advantage would be it works well with low light conditions or even night conditions, like zero visibility at all, since it doesn't necessarily use light, as it doesn't really need light for it to sense objects. And another strength of it would be that it helps separate objects, since each object is detected or is mapped out by the LiDAR sensor in a point cloud. The distinguishing objects would be easier. So as for the limitations, it has sparse data. It has sparse data, especially at long distances. So in this GIF below, as you can see that as it gets further from the sensor itself, it would be there are less and less point clouds, and it's becoming less accurate. And it is quite another limitation would be it's quite expensive than cameras. So the LiDAR sensor itself is more costly, and it requires specialized models and computational resources. Since you're processing different since you're processing different data, like compared to the plain image one, which you're processing 2D images. Here you're processing 3D point clouds. So each pixel or each point is taken into account for when processing LiDAR data. So the, now moving on to the next modality, we have infrared object detection. So infrared, it captures heat signatures emitted by objects, so rather than visible light. So as you can see here, it's a it looks like black and white images since it captures heat signatures uh rather than the visible light. So it works by detecting differences in infrared radiation and such that warmer objects emit more infrared radiation. So this can also be like this can also be defined like as thermal cameras, which are all in grayscale. And yeah, models trained on IR or infrared data can detect humans, animals, or machines used solely by their heat. So uh, in this GIF below, as you can see, mostly the engine portion of cars and humans have emit the highest or are the brightest in this GIF compared to, let's say, the different roads or the inside of cars or the cars that are not running. Since so infrared, the strengths of infrared is it works well in low light conditions since it captures infrared data rather than visible light. It can detect living beings since they emit more infrared radiation, even if it's camouflaged or obstructed. And then it doesn't rely on reflected light. So although the limitations is it has poor resolution and texture, so it's really hard to distinguish bit similar hot objects. So if you have two objects that have the same temperature or are emitting the same IR radiation, it would be hard to distinguish. And again, it's in a grayscale, so there is a lack of color and texture that that can be learned by models or that can be extracted by models. So I introduced the different modalities since that uh, in object detection, uh, different modalities have different limitations. So an idea would be is what if we could combine these different modalities? So if we combine these different modalities, we can possibly have the strengths of each modality into uh, be combined and be put in a single model. So, for instance, plain camera models can have a lidar module built into it so that it can also perceive uh, depth data. So it's able to tell which objects are closer or further. So that's the idea with multimodal object detection. So multimodal object detection basically fuses the different uh, datas that are available in such as datas coming from cameras, LiDAR, radar, or infrared. It doesn't really have to be these types of sensors, but I use this as an example. So since we are integrating different modalities here, uh, we can lever it. Different modalities leverage from we can leverage the weaknesses and strengths and weaknesses of each modality with each other. So like the previous example that I have said, uh, camera data and LiDAR data can be fused together to have both texture, color, and have give it a sense of depth. And yeah. So, but this question now comes up with, how do we exactly fuse modalities together, since they're different in data types. Like for LiDAR, there are point clouds. Images, there are 2D images. Then for infrared, it's basically grayscale images, but with infrared radiation data. So how do we combine these different modalities? So we have something called fusion. So fusion in multimodal object detection, it means combining information from different types of sensors. So like cameras, LiDAR, infrared, and such, so that the model can make decisions that it would be using, so that like it can simulate, like it can be able to determine or it can relate each modality with each other. So when with fusion, there are three considerations that are needed. So we have fusion stage, or when to fuse in a model. We have fusion input, or what to fuse. Then with fusion granularity, or which is how to fuse. So first we'll be starting with fusion stage. So here we have the fusion stage early. So basically, the idea here is that we have an input right here. We have an input right here that's going to be the raw data from images and point clouds. And then it's going to be transferred into the backbone right here. So the backbone would be able to uh, process these images or these point clouds and be transferred it to make extract features from it. So we have each feature. So the early fusion would be fusing the LiDAR feature and the image feature at a feature at the feature level before it is even fed into uh before it is even fed to the detection head or being used for predictions. So this process, or the early fusion, is combining features from different sensors at an early stage, so before they could be fed into backbone or detection head. So again, so the advantages of early fusion is that the model is able to learn uh, the feature of both lidar and image, and they are able to basically correlate with each other, or yeah, basically correlate with each other, so that they can give the detection head accurate a more accurate prediction. So there is an early there is an early like collaboration between the two. And so moving on to the next fusion stage, we have late fusion. So in late fusion, since so as we can see here, we again have the input stage right here. Then these are basically again raw datas of point clouds and images. But then this graph really obstructs the feature extraction stage. But the the idea is that features are extracted from the point clouds and images, and then already fed into the detector. So the detector detects what was extracted from the input images or input data. So there's already been a prediction made by since it is the features extracted from the data has already been fed into a detector. So now after the predictions are made, this is where the fusion occurs. So it's basically just like running two different pipelines and fusing their predictions together. So I guess I can sum it up with like it processes each data point or pipe each modality separately, then it fuses its predictions. Then from there it can the model can decide whether or not uh the model can decide from these two predictions uh the actual output of the detection. So the advantages of this is it preserves unique modality strengths. So LiDAR for it preserves the depth of LiDAR and the texture and color of cameras. As for like compared to the previous fusion technique, which is the early fusion, the depth and color can be lost in the fusion since the model is already learning from the features of both combined. So uh yeah, so some certain data can be lost with fusing late, you're basically running two pipelines. So uh no no data is being lost. So LiDAR is still retaining its depth and the images are still retaining its color and texture. Um as for its limitations, however, it misses like the early interaction between the fusion. So it doesn't even show it here, but there's really no interaction between uh the LiDAR and images in terms of the future state feature stage of it. So there's really uh it doesn't the model can't uh how do I say this? The model cannot extract further features with that the model cannot learn more features that basically combines the two. It's solely relying on the detection between LiDAR and images. Another limitation is higher computational costs. Since basically you're running two pipelines, that's yeah, I'm you're basically running two pipelines, so it has a higher computational cost. So moving on to the next uh and last fusion technique, we have cascading. So cascading basically is one sensor's output is used as an input or is used as prior knowledge to another sensor's pre-processing. So basically here we have the images and it already detected or it's already fed into the detection head with its features extracted. But then with this data or with this detection, it is transformed into a 3D representation of its detection. So basically, uh, after it had a prediction, it's then transformed into a 3D representation so that it is fed into the backbone of uh the backbone of the LiDAR backbone. So this creates a step-by-step or cascade relationship between the different modalities kasi an input of the modality uh can be used as prior knowledge or used as input by the other one. So one modality provides prior information that can greatly reduce the other's search space. So in this case, uh, it can, in this case, it's basically saying that uh, in the prediction of the image, then it's being in the prediction of the image, it's telling the lidar sensor or lidar mode or the backbone to search for this portion only right here, so that it's narrowing down the uh use of lidar itself to a certain area. So yeah, the advantages of this cascading would be that it's guided detection. So since that lidar is computationally expensive, uh, having an image, having an image, detect the location or region of interest in an image and then processing it through the lidar would be efficient, since the lidar is only processing certain portions of an image instead of the entire image itself. And then as for the limitations, however, it is complex to design. So compared to the other two we have, it's fairly simple. It's a fairly simple pipeline. As however, for this, there would be uh, it's quite complicated, since you're getting the prediction of a certain modality and transforming it into to be represented or relate to be related to the next to the next modality. In this case, it would be the input state images being turned into 3D, since lidar data is in 3 dimensions. So that's basically the gist of uh when to fuse. So we have early, late, and cascading. Now moving on to the fusion input, or what to fuse. So fusion input refers to the form or representation of data from each sensor that's get passed into the fusion module. So it's basically asking what exactly are we fusing, since uh do we actually fuse the raw data of the image and the point clouds of lidar, or are we pre-processing it to are we pre-processing it so that it would be easier for us to fuse? So as you can see here in the graph, we have feature maps, masks, and pseudo lidar point clouds for the image branch. And the point cloud branch, we have voxel grids, raw point clouds, and bird's eye view or rear view projection. So for the feature maps, basically it's the intermediate activations of the image backbone. For masks, we have segmentation masks or region of interest areas. And then for pseudo lidar, a depth estimated 3D representation derived from the cameras. So basically the feature map would be basically like the plain object detection using images. For masks, it sets different regions of interest in an image. So it basically detects where the object is. And for the pseudo lidar, it projects the image in a in a 3D uh in a 3D dimension, or it represents the image basically in a 3D dimension. As for the lidar, we have voxel grids, which are 3D grids filled with points, like 3D pixels. So it's basically like you're doing an object would be separated into different cubes, and each cube has a value of many different points, so that those are voxel grids. Raw point clouds are basically just points of basically points that has been generated by the LiDAR sensor. And for bird's eye view and RV projection, uh it's basically pre-processed raw points or data clouds, so that it has a top view. It can be represented from a top view. These are just Not all of these are used. These are just some of the different pre-processing or different types of inputs that can be that can be used in Fusion when it comes to fusing camera and LiDAR. For different modalities would then different modalities would require different pre-processing techniques as well. So you won't be using bird's eye view or raw point data clouds for different modalities such as IR and such, since this is specific to LiDAR itself. So yeah. As for the as for answering how to fuse, we have fusion granularity. So it's basically asking how detailed or fine-grained the fusion is. So basically, this would be if you're fusing two modalities together, an example would be image and LiDAR. Would we go pixel for pixel in terms of fusing them? Like each pixel of an image would be corresponding to each a point cloud in the LiDAR data. That would be the most fine granularity. Or we would be pre-processing these data to be more generalized and not necessarily be too fine on how we are going to fuse the both data sets. So I the main thing to consider here is that fusion granularity is here because of how complex do we want the computations to be. If we're matching each pixel of an image to a point cloud in a LiDAR data, that would be a lot of different computations, since it would be plenty massive amounts of data that needs to be related to each other. Other aside instead of instead of doing that, we could generalize it by using voxel boxes, which is the splitting of LiDAR data and partitioning them into cubes, so that each cube corresponds to that region, and we're matching images from that region to voxel boxes. So it's basically how fine do we want the fusion to be. So yeah, then the finer the granularity would be, it would lead to more higher computation, but it would be more accurate. So that's it with fusion. Here we have some multimodal examples of multimodal object detection models. These were picked uh, to also represent the different fusion levels that was discussed earlier. So it would be early, late, and cascading. So first we have is the BEV fusion, which is a representation of the uh, early level of fusion, since that here we have it basically uh it basically it basically transforms the camera stream. So we have two streams here. We have the camera stream and the LiDAR stream below. So the camera first is the feature it uses six different cameras. So front, back, then two at each sides. And then features are extracted from it from here. And then from there, it is pre-processed to be in a bird's eye view in a bird's eye view representation. So it is done it's represented like in bird's eye view since the LiDAR is all the main goal of Bev Fusion is to represent both data modes of data into a bird's eye view. So like imagine yun like imagine if you're having a hard time picturing bird's eye view, imagine if you guys are familiar with League of Legends or any MOBA like Mobile Legends, it's basically a top down of your character. In this case, it's a vehicle. So the camera is represented in a bird's eye view, and the lidar is represented in a bird's eye view as well. Then features are extracted from this, and the fusion happens. So before it is fed to a detection head, it's already pre-processed, and and the the features are both combined and is then fed into the detection head where the final detection would be made. So the benefits of this is that it keeps it simple. Uh it's really easy to understand that there's pre-processing happening here, then it extracts features from bird's eye view camera, and here it extracts features from lidar bird's eye view, and then it's eventually fused together and fed into the detection head. Then it's also quite flexible because it can both work with camera only or lidar only, or in this case it can also work with both. And it's also robust in terms of it performs well even with one sensor missing or degraded. But there are some limitations when it comes to this approach. One would be there is a loss of fine visual details since the cameras here are pre-processed and represented in a bird's eye view format. Fine details of texture and color can be lost since you're essentially looking at it from a top-down perspective already instead of the perspective of the camera itself. So certain certain features such as texture and color may be lost in due to that pre-processing. Another limitation is heavy on computational cost. Imagine having 6 different cameras and using all those data to transform it into a bird's eye view representation is really a lot of computations to be done. And not only that, but you'll be also fusing it with with the lidar data itself also. So moving on to the next model, we have transfusion. So transfusion would be one of the examples of late late fusion. So it's already made a uh detection or a prediction, and then it fused those two detections together to create a final prediction. So the lidar feature so they pre-process point clouds right here, and they pre-process it so that it's also represented in a bird's eye view. They also gather image features from here, from the 2D backbone. And then with the use of image guidance, it does something called query initialization. This basically in an image, this basically shows where uh certain objects are, so that the lidar itself would only focus on those specific portions. It's then it does a prediction of its own using these queries, as well as the image doing a prediction of its own. And both of them will be fused together to create a final prediction right there. So the advantages of this is that it's LiDAR driven, so it keeps a strong spatial structure, as well as keeping the camera structure as well, since both of these technically have I basically has different pipelines, so some features are still retained. Um, but the limitations, however, is that the fusion of both is not that deep, since again we're dealing with fusing predictions of both camera and LiDAR. The features don't really have was not really it wasn't introduced or fused early. So it's the relationship between LiDAR and camera, the relationship between the features of LiDAR and camera is not that deep. So there. So moving on to the last, which is deep interaction. Deep interaction is it uses both camera and LiDAR data, but instead of fusing them early or just late, it actually uses a cascading fusion. So it basically, I know it's pretty hard to understand this type of architecture, but it's basically uh, reintroducing past data of image and LiDAR to to help uh to help refine the prediction of both. So as we can see here in A, uh, as we can see here in A, it's basically using both the image and LiDAR pipeline are exchanging informations, and it helps them refine it helps them to refine their predictions by exchanging information frequently. And then as for the B portion, this would be basically how it is fused in the pipeline, and uh how it is fused in the pipeline and outputted in the detection head. So the advantages of the cascading interaction, or in this case with deep interaction, it refines features across like multiple stages, since they're constantly switching information. And then for uh since it's also two different branches or two different pipelines, it basically has its own features, and it builds upon the different information that it was passed to by the other branches as well. As for the limitations, it is computationally heavy as well. Uh, since you're running two different branches and exchanging information, not even fusing them yet. So it's really uh it's computationally heavy compared to the previous one, since here you're fusing they're exchanging information in a single step, while this it's a constant exchange of information. So, and it also has complex architecture, like compared to the previous ones. This is harder to understand since there are a lot more things going on. So moving on to the advantages and disadvantages. So it's improving accuracy, since uh in multimodal object detection, it leverages from the strengths of each mode. So while yes, some modalities lack certain things, it can be leveraged. It can be leveraged of from a different modality that it has been fused in. So robustness in it's also robust in adverse conditions since by adding so by adding different modalities, you can basically tailor it to you can basically tailor it to the problems that the original model was having trouble with. It has better object localization since, for instance, you're using LiDAR data. It provides spatial measurements, basically, yeah, tailoring it again to the needs of the problem or the model. Then it's able to generalize better across varied domains, urban, rural, day and night. As for the disadvantages, it has high computational overhead since you're introducing different computations like pre-processing the data or the general fusion. It introduces a lot of added stages or layers to the pipeline. So it has high computational overhead. It's also difficult to perfectly align and synchronize data from different sensors in real time. So data such as, like in this instance, camera and LiDAR, it's really hard to perfectly sync them up. Then an increased system cost since you will need more sensors. This would mean that it's more expensive. And we have data fusion complexity. So there we the ideal scenario would be that having perfect fusion between two modalities would result in the data being homogeneous, but again, that is far too complex since there are a lot of variables that are being taken into account for when it comes to fusing two modalities together. And lastly would be the lack of large scale multimodal datasets. So datasets would require the multiple sensors or yeah the datasets would require multiple sensors uh such as RGB, LiDAR, thermal, or yeah. So when you're finding datasets to train and test models on, it has to support the different modalities that the model needs. So it's really hard to find datasets. As for the use cases and applications, I'll just go over this quickly. So we have autonomous driving systems. Here it's uh, combining image data and LiDAR data. As you can see, it's using image data for different textures and color while still having that perception of depth to it provided by the LiDAR. And here we have HyperDenseNet, which fuses MRI and CT to search for brain lesion segmentation. And then lastly, we have Fusion GraphNet, which combines uh, uh, RGB camera or images and depth for robotic class planning. So basically, the most efficient way for objects or for the robot to grasp certain things. So yeah. So that will be all for my presentation, and thank you. And here are my references.
Thank you for the presentation, Ryan. The floor is now open for questions that our listeners might have of the presentation. You may send your questions via the chat, or if you want, you can also raise your hand so that you can be acknowledged. Anyone? Maybe I'll start the first question. Um, do you think there's a correct set of modes that you have to combine given a certain problem? Like pag ganito yung problema, if this is the problem, this will be the modes that I have to combine. But for a different type of problem, I also have to change the modes that I'm going to combine.
I would say, sir, yes, since generally the idea of combining different modes is filling the gap of the problems of the mode like a certain mode that you're currently using right now. So like for example, in this case, basically the problem with images would be that it lacks depth perception. So you won't really need you to use the modality of infrared if you want to solve the problem of depth perception, since infrared would solve like occlusions in certain settings and visibility problems. So different problems would require for different implementation of or different fusion of modalities so that it can fill in the gap of the problems of the modes that you currently have.
Okay, so there's no silver bullet, no, na one solution fits all for
Yes.
this type of solutions.
Yes, sir.
Okay. I have like one part of your presentation, I was able to relate that to one of the things that we're currently doing. I think Carlo is here. Um, we're in his thesis, I think we're kind of doing something on the lines of cascading in terms of the fusion. What we're doing there, but this is for a different type of topic on agriculture. So in cascading, what we're doing there, although we're not fusing different modes, we're training the same model but on different types of annotations. So just to give you an idea for all listeners, we have this input image of a, let's say, leaf. Okay. Then we pass it through one convolutional network. The annotations are yung what we're trying to detect are very small insects. Something like that. Very small insects, which are very hard to detect when you are using an object detector. So instead of directly um, identifying or detecting those small objects, what we did is the first set of training, what we did is we trained it on clustered annotations, meaning we're trying to detect clusters of the insects, not the specific insects, but clusters. So we're trying to determine where to look, basically, similar to what this model is trying to do. Now, we're trying to guide which part of the image should the next network look at so that we can be more guided in terms of our detection. So at the first stage, we're trying to detect the larger clustering of multiple insects. But in the second part, in the second section of training, we're already identifying those smaller insects. We're trying to zoom in on those regions detected by the first stage. Okay? So that would be our search space. We're limiting our search space so that we can detect better the smaller objects, in this case, insects. Okay? Any questions? If you have none, can you please raise your hand so that we can end the lecture for today? Okay. I think in general, there are no more questions from the listeners. I guess that ends our lecture for today. I thank Ryan for the presentation on multimodal object detection. So as I mentioned, this is already our last presentation for the term. We're not going to have any lab-wide specific activities so that we can focus already on our thesis. I thank everyone for attending this session and also attending all the other sessions that we had all throughout the term. And we hope to see you again next time. Thank you, Ryan, for the presentation.